Welcome to our live webinar, How to Get OPC UA in Your Device. Today's webinar is hosted by Automation.com and Softing Industrial Automation. Thank you for joining us. My name is Renee Bassett, Chief Editor of Automation.com, and I will be the moderator for today's presentation. Before we get started, I would like to take a moment to acquaint you with an important feature of this GoToWebinar technology that we've all logged into. We encourage you to ask questions. On the right-hand side of your screen, you'll see a Questions tab, and all you have to do is click in the text box, type your question, and click Send. All submitted questions are only seen by the presenters, and at the end of the presentation, we will answer as many questions as we can while keeping the overall presentation time to 1 hour. If we run out of time, the questions will be forwarded to our speaker for future response. Also, please note that at the end of today's program, we'll ask you to complete a brief survey. We appreciate your time giving us feedback so that we may improve your next experience. Today's presentation is about how to get OPC UA in your device. OPC UA is the most important communication protocol for Industry 4.0 and the Industrial Internet of Things, or IoT. Use of OPC UA ranges from the SCADA HMI level down to the field devices. With the FLC initiative, the OPC Foundation started to define OPC UA for field level communication. And a lot of OPC UA companion specifications have been created for the device level. This webinar will show you how Softing's uaToolkit embedded can help you get OPC UA in your device. Our speaker today is Thomas Rummel, Senior Vice President of Engineering and Product Management for Softing Industrial Automation. So, without further ado, take it away, Thomas.
Thank you, Renee, for the introduction. So, I will start with a short introduction of myself. So, my name is Thomas Rummel, as already said. So, I'm working for Softing Industrial here in Munich, Germany. And I'm responsible for the product management and the development in the business unit data networks. I work with OPC since now 21 years, and I'm member of the OPC Foundation TSE, the Technical Advisory Board, and also listed as an OPC expert on the foundation pages. So I'm also a member in several OPC UA working groups like the Core Specification Working Group or the P&O Working Group right now. But now coming to the agenda of today's webinar. So the first 3 sections will give you an update on OPC UA and the motivation why you should run OPC UA in embedded devices. The last section then will give you an introduction into Softing's UA embedded toolkit product, which allows you to implement embedded OPC UA application. But now let's start with a short introduction into OPC UA and its relation with Industry 4.0 and IIoT. The OPC UA specification now exists since 13 years. So it was released the first time in 2006 with the version 1.0, and then you see here on the timeline we had then almost every 3-4 years another release, and the current release is the version 1.04, which has been released end of 2017 starting 2018. OPC UA in the meantime is widely used in many products. The main facts about OPC UA are listed here on this page. So it's platform independent standard for communication, which means you can run it on almost every device having an IP stack running. It supports the definition of information models, which you can discover during runtime from the server or get the information passed over offline in a file. For the communication, it defines abstract services for accessing the information model and, of course, the values of variables which you can read and write. It defines in addition then the technology mapping of these abstract services to real communication protocols. And in the meantime, it supports all common communication schemes for industrial protocols, so the client server and the publisher subscriber communication scheme. It supports a secure and robust communication, especially security was built in from the beginning as a main feature of OPC UA. Since the first version, OPC UA is supporting client-server communication. So client-server communication means that an OPC UA client sends requests to an OPC server requesting the execution of some service. And then the server is doing this execution and sends back the answer in a response. Also, part of this client-server communication is that a client asks a server to publish notifications, and they also will be sent back as a response to a publish request the client sends to a server. As said, the interface between the clients and server is a defined set of services a client can call on a server. The second communication mechanism OPC UA now supports with the version 104 is the publisher-subscriber communication. Here, the publisher and the subscriber do not directly exchange requests with each other. So they normally don't know each other. So a publisher sends messages out to any subscriber which are listening. And subscribers which want to get information from the publishers, they are connecting to them and get then all published messages that contain data or contain event notifications from the publishers. So there could be an explicit middleware, as you can see it here in this picture, or you can have, which is normally called then a message broker, like you have, for example, from MQTT, or you can have publisher-subscriber communication without an explicit middleware. Then typically it's done by the network infrastructure. For example, if you're sending messages to UDP multicast addresses. Also, here in the publisher-subscriber communication, OPC UA supports security. So the messages sent from a publisher to the subscribers can be encrypted and with that secured on the communication paths between the two. And for the configuration of the data published by a publisher and the data then received by a subscriber, OPC UA has defined a configuration module which allows you to configure the published data, for example, by services again sent out with the client-server communication. The main difference from OPC UA to other communication protocols is the possibility of information modeling. So that's really the big difference to other existing industrial communication protocols. And the address space of an OPC UA server, that's the vehicle to do the information modeling. So here you see on the slides the base building blocks of the address space of an OPC UA server. So every information modeled is represented as a node in the address space. And a node always has some attributes which describe the node and then references to other nodes which defines the relationship between these nodes. So, and with these base building blocks, the whole address space is built off. And that's used to model objects and variables and methods in the OPC UA server. And besides this instance information, you can also model type information in an OPC UA server. So, and they both together are part of the same address space. So you can define object types, variable types, reference types, and data types within an OPC UA server. Of course, the OPC UA specification comes with a large set of standard defined types, but every server can define its own types and publish this type information, this meta information, via the OPC UA address space. And OPC UA allows every client with its services to browse this address space online. So you can discover all this information online, and then you would see something like here in this listed on the screen. So that it's below the root of the address space, you see a node which is called types, and below that you have all the type information of your OPC UA server, and below the objects node you have the instance information of your server. Besides this online browsability of the address space, there's also a way to get an offline representation of the address space. And this offline representation is provided in XML files. And these XML files of OPC UA address spaces are called node set files. And for all defined nodes, for example, of the OPC specification, the OPC Foundation provide node set files which are describing these address space information. OPC UA is generally defined as an abstract set of services and data sets. But in port 6 of the specification, the mapping to concrete transports and method encoding is defined. And here you see the complete list which is currently defined from the OPC UA specification 104. So you have different transports and encoding for the different communication schemes. So on the client server side, you have the first one is using TCP communication and the UA binary encoding. And that's the mainly used protocols currently if you talk about OPC UA. Typically an OPC UA server is implementing that as a default protocol and encoding. But in addition to that, you have in the specification also defined a protocol mapping for HTTPS and WebSockets. And besides the UA binary encoding, which is really binary data, we have also an encoding defined for textual representation of the data, one for XML and one for JSON. On the publisher-subscriber side, you have defined transport for UDP with an encoding called uaDP. That's also a binary encoding, and that's the standard encoding used, let's say, on a factory floor for PubSub. The other mappings are more for communication through cloud services or to IT services. So you have an MQTT and an AMQP transport defined either with a binary encoding of uaDP or again a textual encoding with a JSON transport. So the Industrial Internet Consortium, the ISE, it mentions OPC UA as an integral part of its connectivity framework. On this side, you see the mapping of the different OPC UA ports to a communication framework. So on the network level, currently, you have always the internet protocol, so IP. That will change when the mapping from OPC UA to TSN is released. So then you will have on that level also TSN communication. On the transport level, you have the communication protocols on top of IP, so TCP and UDP, and the different other transports like HTTPS and MQTT. Then on top of the transports, now the ISC model defines the framework layer, which is represented from OPC UA on the one side by these abstract services and the data sets you can define for publisher-subscriber communication, and the information model, which is presented in the address space. OPC UA provides an additional difference to other communication protocols, And that's this top section you see here titled in the ISC connectivity framework as distributed data, interoperability and management. So with OPC UA, you can even define more as an information model. You can really define your own private or public companion specifications, which allows you to really pass data with enough meta information that you can interpret it in a client and know exactly which kind of information, which kind of data you're passing over. So it's enriched with a lot of metadata, which allows you to, for example, have a semantic intro being passed over from a server to a client. Also in Industry 4.0, OPC UA is mentioned as a protocol you have to realize in your device. So for the communication, OPC UA is a mandatory protocol you have to realize. And for the service and conditions, OPC UA is stated as an optional protocol, so where you can use for passing over statuses and error messages. So OPC UA covers all the communication and information layers, which is described in the RAMI 4.0. And you see here on the right side the document from the ZVOE organization, which is defining these criteria you have to implement if your product should fulfill the needs of Industry 4.0. So that was a short overview on that one. If you want to have more information about the interoperability of OPC UA with Industry 4.0 and the IIC consortium, there's a very good brochure of the OPC Foundation you can download from that URL. So that in addition describes this compatibility with a lot of examples and give you some examples how to use it with IIoT. Another interesting initiative for embedded OPC UA is the OPC UA for field level communication. So that's an initiative which was started in November 2018, so it's not long ago. So here in this picture you see on that circle what is the topic the FLC initiative is concentrating on, and there's exactly two things which are in the focus of this specification which will be created in this initiative. So here with the point 5 you see communication between two controllers on a factory floor. So controller-controller or machine-machine communication. With point 6, which is also part of the FLC initiative, the communication really on the field level is addressed. So the communication between a controller and some field devices being installed on a field level. So this will include standards for simple I/O devices, for motion control, for safety systems, and of course functionality like a system redundancy. You see here on that side the numbers of automation vendors which are supporting this initiative. So it's not the complete list, but it already mentions almost all main automation vendors like Rockwell Automation, Siemens, Schneider, ABB, Yokogawa. So there's wide support for this initiative. So another picture which illustrates this huge support is here a picture taken from the kickoff meeting, which was held in January this year at Siemens AG in Munich. So at this kickoff meeting, you had 90 attendees of 38 companies visiting here this meeting, and also in the follow-up meetings now, which has been take place on several locations around the world. It always had been more than 50 people working here on this initiative. Also here, the OPC Foundation provides a brochure which is describing a little bit more details on the FLC initiative, so you can download it also from the OPC Foundation webpage. So, and of course, that is describing how this should be achieved. So with OPC UA, using PubSub client-server communication with or without TSN. In the first step, the FLC group currently is defining. They will concentrate on the controller-controller communication, and then on the next steps, they will address then the communication between controllers and devices of any kinds. In the next session, I want to give you an overview of the OPC UA companion specifications which are dealing with devices. And there's especially one specification which is the base for all of the companion specifications which are done for devices. So that's the OPC UA for devices specification, which is done, which is written by the OPC Foundation. So that's the part 100 of the OPC specification, and it is existing since 2013. So there, the version 1.10 was released, and this year, so last month in April, the latest version, so the next one, the version 1.02 of the OPC UA for devices was released. So that's already now available for download on the OPC Foundation web pages. In the version 1.0, these companion specification only included one information model, and that's the one you have here listed on the first line. It's a base model which describes how to model devices in a unified view, and mainly representing asset information for these devices. With the version 1.01, the two other models have been added. They are much more special. So there, the OPC Foundation integrated needs, functionality needs, which came up by the FDI specification into OPC UA for devices. So all these parts are optional for implementation. So the first one is a device communication model, which allows you to model the communication between devices. So you can model networks. For example, you can model there Foundation field bus network or Foundation field bus devices with the communication paths between these devices. And so you can build up logical communication topology. The third model is very special to FDI, which allows you to integrate a host model, which is required if you want to parameterize devices. So you have an online and offline view. So that model is normally not used in these companion specifications, which are built on top of these part 100 of the OPC specification, which is not FDI. Of course, FDI is using that one. So in this base model, OPC UA for devices defines standard interfaces for asset information, and that's one of the big advantage here. So if you use this OPC UA for devices, you have a standard way to, for example, provide the asset information from a manufacturer's point of view for your device. So there, for example, the manufacturer name, a URL for the manufacturer, the model, product codes, revision of hardware or software, or serial numbers are provided. And you get all this information from all devices in the same way by this iVendor nameplate interface. The specification also defines a way to get information about the device asset from a user, so from the company who is using the device in an installation. So like an asset ID or a component name you can give to the device when you install it. In addition to the asset information, the OPC UA for devices also provides interface for discovering the device health. So this device health is modeled after the Namur recommendation 107. So you can get states like a normal, failure, check function, off spec, or maintenance required of the device. So you have really these main health categories you typically have on these device levels. In addition to that, you can also provide support information on the device like device description files, documentation, images, so which also can be transferred via OPC UA. On this picture, you see an overview of all the collaboration the OPC Foundation has currently. So I already mentioned here the Industrie 4.0 and the Industrial Internet Consortium, but maybe you see here also agreements where you know, so you have different areas like in the energy section, you have here consortiums like Energistics or also a mapping to IC 61850. On the factory automation, there's a lot of companion specifications being done right now, for example, like with the VDMA or the OMAC. Also on an IO level, you have companion specifications with all the different other field buses where some mapping between the field buses and OPC UA is defined, but also in other industries like here HKI, which is for kitchen equipment, or MDIS, which is for subsea automation, or BACnet for building. And also, of course, in the process automation, you have companion specifications done with the FICOM group or the open group together, or with Namur I mentioned before. The most active organization defining companion specifications is the VDMA. So it's the Machine Vendors Association. So currently they have more than 20 companion specifications in work. Some of them already have been released, but most of them currently are being defined. So the VDMA has selected OPC UA as the standard communication protocol for machines. You see here a list of machine types which currently are in work for companion specification. The one which was really the first one they worked on is plastic and rubber machinery. So you may know the Euromap specifications, and for these Euromap specifications there already exist released companion specifications for OPC UA. But also besides that, there are companion specifications for machine vision devices. Also now for robots, the VDMA has defined a companion specification which is very close to be released, for powertrain equipment, for weighting equipment, and a lot of other machines. Currently they are in development, and they will also start a lot more others. So their plan is to really have, for all the different machine types, companion specification you can implement as part of your machine, inside the machine, as an embedded OPC UA server, which is then representing the information, the data of this machine or the device itself. Okay. Before now coming to the softing product which help you doing an embedded OPC UA server, we want to start with some poll questions, as Renee already mentioned before. So now I would ask you to please select one of these answers for the questions so that we can pass through this poll. Okay, so definitely there's a big interest in OPC UA embedded, so I think the next section then also will give you some hints on really how you can really implement OPC UA. But now the next question will come. That's about PubSub. So that's a quite new specification. Okay, that's like I expected. So as said, so it's on the market now since, or it's released since 1 year, and it's slowly starting really getting more and more interest in the market and in the requirements you see. Okay, and thank you for answering these poll questions. I now want to continue with the next slide, which is really then give you some intro into Softing's product uaToolkit Embedded, which helps you realizing embedded OPC UA applications. On the first slide, I want to give you some introduction in all toolkits Softing is providing. Besides the embedded toolkit, Softing is also providing a toolkit for .NET and C++. And here you see the automation pyramid. So of course, the C++ and .NET toolkits mainly focusing the higher level of the automation pyramids like the ERP and the MES level. On a control level, we have two SDKs, two toolkits, which allows you to create application. On the one side, it's the C++ toolkit, which is mainly addressing bigger controllers, and the embedded toolkit, which is designed for smaller controllers, mid-sized controllers, where you have to take care about the memory footprint of your applications. And of course, it addressing the device, the field level, with devices on that field level, which are only handled with our embedded toolkit. Of course, on these two levels, the publisher-subscriber communication is always an important topic for deterministic communication between the devices. Now I take a closer look to the uaToolkit Embedded, so to the product. So it's portable C source code, and all features of our product are part of deliverable. So you get source code for all the features and all the platforms supported. It's delivered by a download from our website. So simply on the download side, you have to insert uaToolkit Embedded, and then you can download from there. The license we have for this toolkit is a single seat developer license, which comes together with a mandatory 3-year maintenance agreement, which includes all updates on the toolkit. You're allowed to freely deploy all applications you have built with the uaToolkit Embedded without any restrictions. And also, if you stop maintenance, you still are allowed to build new applications and distribute them to your customers. We are providing a trial version in the download queue. So that's well for PC Linux, Raspberry Pi Linux, and Windows. So, and you can program with this trial version as you can do with the full license, but the trial runtime is limited to 90 minutes. So after 90 minutes, the communication of the application will stop. Target systems of our uaToolkit Embedded are going from really small device processors like a Cortex M3 or a PIC32, from that level to a level you typically use in gateways or small controllers, which are Cortex-A or Intel Atom E processors. So examples platforms we are supporting with the uaToolkit Embedded you see here on this page. So on the left side you have an interesting wireless chipset. So it's the Espressif ESP32. So it's a processor which comes with 520 kilobytes of RAM and 4 megabytes of flash, which has a free RTOS with an LVIP stack, and for encryption it used embed TLS. That's an example for, let's say, the lower end of the target systems we are addressing with the uaToolkit Embedded. More on the middle, higher end, you have something like our Softing gateways. So that's on hardware platform which is using dual-core Cortex A9 processor with 120 megabytes of RAM and 16 megabytes of flash. So we have there an ECOS operating system, also with an LVIP stack, and for encryption we are using the OpenSSL library. On this slide you see the detailed features of the uaToolkit Embedded listed. So one important thing for an OPC UA SDK is the the profiles which are defined in the OPC UA specification, which are supported. And the uaToolkit embedded supports the 3 profiles which are defined for embedded devices. So the smallest is the nano-embedded device server profile, then the next one is the micro-embedded device server profile, and the biggest profile for embedded devices is the embedded UA server profile. Our SDK is OPC UA, OPC Foundation Lab certified. We support the server security and publisher and subscriber functionality within the toolkit. Also for these information modeling, we have a tool which allows you to import OPC UA node set files. So from the data types which are supported, we support built-in data types, one-dimensional arrays, custom structures, and enumerations. Like I mentioned before, you can build up your own data types in OPC UA, so every server can do that. So you can store the address space in Flash, or you can change it dynamically on runtime. You even can mix both mechanisms of doing it. So we need one set for, or one task for client-server communication, one optional for the subscriptions on client-server side, and one for publisher and subscriber, depending what functionality you want to implement. We deliver platform layers for Linux, FreeRTOS, ECOS, and Windows. We have also partners which are providing additional platform layers for the uaToolkit embedded. So we have one in Japan providing micro-item support, and we also have support for Mentor Nucleus operating system. Also, our customers do own ports to operating systems, so we have customers which already use it on Emboss, QNX, and VxWorks. So we support 2 different encryption libraries, so that's the OpenSSL and the Embed TLS, which is especially designed for the embedded use. Here you see an example of the memory footprint you need or can achieve in your application when you're using our uaToolkit embedded. So the uaToolkit embedded in general is designed for a very small memory footprint, and it allows you to select individually the single functionalities, and with that allows you to optimize the needed memory footprint, especially for the code, to a minimum. And you also can find limits for the RAM usage of your application. So now these pictures show you some examples of the needed memory for the different profiles on the left side. So if you want to build an application which is supporting client-server communication and is implementing the nano embedded device server profile, there we talk about a code size and a size for static data of 240 kilobytes. And for the runtime data, you need a maximum from around 40 kilobytes for runtime data. Of course, the numbers you see here for the sessions and the nodes, that's not a strict limitation, but to be able to give you some numbers here on the sizes, we have to give you some examples. So we don't have any limitations in the number of nodes and the numbers of sessions in the toolkit code itself, but you can define it in the application, your upper limits on that. For a micro-embedded device server profile, which is adding these client-server subscriptions to the nano embedded device server profile, there we end up around 285 kilobytes of code and data, and on the runtime you need more because you have to hold all the information for the subscriptions. There you end up in an area of 120 kilobytes of runtime data. These 2 profiles don't need or don't mandate security. The embedded UA server profile is adding security and is adding methods, and in addition, with that profile, you need to implement the complete OPC UA address space in your server. be compliant with that profile. And therefore you have here the big increase for the code and static data. Only 600 kilobytes of that 1400 kilobytes of code and data are used by the standard OPC UA address space you have to provide with that profile. Of course, the other parts is needed for encryption support, so which will be used for the security implementation. On the runtime side, you also need more runtime memory, so you end up here around half a megabyte of runtime data. For independent from the client-server communication, you also need memory, additional memory, if you want to implement a publisher or subscriber. So both are in the area of 150 kilobytes for code and static data and around 10 kilobytes of runtime data. Even if you build an application which is a combined subscriber and publisher, the needed memory for code is not increasing very much. Here you end up around 170 kilobytes memory usage. So now I want to give you some more information how the uaToolkit embedded is supporting information modeling. So the first step for information modeling is that you are creating an information model. So you can use a tool like I show here, the Xiomi tool from Siemens, which allows you to create an information model for OPC UA. So and this editor for nodeset files allows you to create these XML nodeset files which are representing an OPC UA address space. Of course, you can also use nodeset files from standard companion specifications to be used in the uaToolkit embedded. So the next step is to create C source code out of these nodeset files. That's done by the nodeset import tool we provide with the toolkit. So that is reading in these XML files and creating directly C source code files out of that one. Here in that example with the trial version, that's compiled here with Visual Studio on Windows, but of course also with the full versions, these generated C code files can be compiled for your embedded devices. And then that already creates the application code you need for realizing this information model. Here you see an example, OPC UA client, so that's the Softing data feed client. You can also download for free from our website. And there you see here, you again have the same information model you before modeled in the Siemens tool. In that case, some test device with some DI data. I already mentioned before, the uaToolkit embedded is OPC UA lab certified. So we passed lab certification with it last summer. So we did the certification tests for all 3 profiles you currently are able to certify for the client-server communication. Unfortunately, there's no certification program for the PubSub yet. So we are certified for this nano, micro, and embedded UA server profile. On the next slide, I want to give you some impression about the performance you can achieve on a device with the uaToolkit embedded. So we did some tests with an old Raspberry Pi running with Linux, and that has an ARM11 processor, which is more or less in the middle of our target range from the platforms. And you see here in the chart the numbers of values you request with a single call. And if you have multiple values, so if you request 30 values in one call, then you come up to a range of 130,000 variables you can read or write per second from this OPC UA server running on that device. Even if you turn on security, which means every message between the client and server is encrypted, you still come up to a level of 90,000 values to read per second. Of course, these old Raspberry Pis not supporting any encryption in hardware, so it's all done in software. So if you have a hardware encryption, this gap even gets smaller. So currently, you can download the version 1.20 of the uaToolkit embedded from our website, but we are already working on the next version, which will be the version 1.30, which is planned next quarter to be released, and that will add events and alarm and condition functionality to the toolkit. Additional features we will implement this year and next year is a basic client functionality, and then some extensions to our publisher and subscriber. We have already as a part of the uaToolkit, and another functionality is then historical data, which then will come later in 2020. We also want to add an additional platform layer for the emboss operating system. Okay, I want to close this webinar. There's a summary of the uaToolkit embedded. So here you see the advantages of it listed. So it enables a rapid development of embedded OPC UA applications. So either with client-server or publisher-subscriber communication or both. So you have a fast time to market for OPC UA in your sensors, devices, or controllers. It's platform independent with a very small footprint, really designed for being embedded into devices. And you have an optimal total cost of ownership through our license model, which is really a single-seat developer license, so you don't have to do any runtime licenses on your devices. So, thank you for your attention. So now we'll open for your questions.
Yes, thank you very much, Thomas. We will take some audience questions now, and as a reminder, you can submit your questions in the panel of the GoToWebinar interface, and we'll answer as many as we can with the time remaining. Thomas, we have a couple of questions asking about OPC UA in general. The first one is, why should I use OPC UA instead of a web service and a REST API?
Yeah. Okay. The big difference between OPC UA and really web services is that OPC UA defines you a standard way for this information modeling. So not only the way how you are transporting the data is defined, also a description of the metadata is you get with OPC UA. So with OPC UA, so you get the transport plus a way your application can define which kind of objects, which kind of variables you are providing in your device. And of course, as I had a slide before, you can also use web services. So you can use HTTPS or WebSocket communication, even with OPC UA.
The next question is, does OPC UA offer native support for device description or DD files?
Yeah, so the device description files, if you want to have, let's say, the device description on OPC UA are these node set files. So you don't have a device description like you have on Foundation Fieldbus or HART or Profibus PA. So you have these XML files which are including an address space. So you also can have a node set file which is including the offline representation of the address space of your device. So with these XML files, you can do an offline integration like you do with device description files and already have all the variables and the descriptions and the types of these variables available in an OPC UA client which is supporting reading in these node set files. So that's the offline representation of it.
Okay, thank you. Now, a question more specific to your tool. I have an embedded operating system on my device which is not on your list of supported platforms. Can I use the SDK with it?
Yes, of course you can use it with it. So of course we have only a limited set of operating systems we are supporting, but our toolkit will run on each operating system which is providing some basic functionalities we need. So it's an IP stack, it is some inter-process communication like a mutex, and you have to be able to start on task or thread. So that's the main functionality you need for something like a nano profile. If you want to add security and encryption, you need some encryption library on your platform. And we have currently the two we support is the OpenSSL and the Embed TLS. I think that's the two most important libraries on the market, and especially the Embed TLS is really designed for the embedded use case. But also others can be integrated. And what you'd have to do there is simply edit the platform layers and adapt it to your operating system and encryption library.
Okay. Also specific to your tool, does Nano Profile have global discovery server push model?
It's not mandated in the Nano Profile. So the GDS support is not part of any of these embedded profiles. But you will be able to add GDS support with our uaToolkit embedded next year when we are implementing the client side. Typically, you need also for these discovery services, you need also some small client functionality in your application to register your server. And the rest of GDS is then providing the right sets of methods which you already can do with our uaToolkit embedded.
Okay. Another question. Do we need to go for an OPC UA certification once a stack is integrated with our embedded application?
Yeah. So the certification for OPC UA is like with all other communication specifications. So it's not on a stack level, it's always on device application level. So you can only certify a complete application or a complete device. So a certified stack, of course, helps you to get through the certification because, the stack is doing everything correct on the OPC specification side. But it's always the combination of stack and application which is going to be certified, because in your application you also have to fulfill some of the rules to be compliant to the OPC specification. So it's always the combination, yes.
Okay. What is the difference between using OPC UA stack directly in the embedded software instead of using a hardware module with OPC UA server converter?
Of course, with an SDK like ours, you can implement, or you have full control over the OPC UA application and the information model you are providing. If you use some predefined module with an OPC UA application in this module, you always have a limited interface between your application providing the data and the application which is pre-built providing an OPC UA server. So it will always be a subset of the things you can do, and typically you cannot do something like creating an application which is compliant to a specific companion specification.
Okay. One viewer asks, is it possible to use OPC UA server in Amazon or other cloud spaces?
Yes, so especially in Microsoft Azure Cloud. So there you have some support for OPC UA because Microsoft was really integrating OPC UA heavily into their IoT solutions. But of course, on the communication side, all these services are using some internal communication mechanisms. But you can, for example, pass through OPC UA services through Azure Cloud. But typically, if you want to push data to the cloud, you are using protocols, transport protocols like I mentioned before, AMQP or MQTT, which allows you really then to send OPC UA data with the OPC UA encoding with this OPC UA protocol directly to an IoT hub, independent if it's Microsoft, IBM, or Amazon.
Okay. Regarding your tool, does the uaToolkit support reverse connect, meaning OPC UA server established as the connection?
Yeah, so currently we don't support that. Yeah, but it's on our list to do's. I know that's an interesting feature, especially if you are considering security and in an installation, because there you can use more stricter firewall rules if you are creating a connection not from a client to a server. With the reverse connect, always the server creates the TCP connection and calls outbound to a client the server already knows. So we will add that during the versions of next year.
Okay. Another viewer asks, do you have PubSub already ready?
Yes, yes. So we have PubSub ready since already a year. So we are the only commercial toolkit which has a released version with a publisher and a subscriber being part of the toolkit. So okay. You can take it, download it, and build a publisher, a subscriber, or both in an application.
Okay. And one last question specific to your tool. The user asks how the single license works. If you have one developer and 10,100 devices to be built, are they paying for only one license?
Yeah, they pay for only one license, but then you have a really good developer to build that many devices. Typically, we are one license is per developer seat. So each developer you have working with OPC UA, with our toolkit, there you need a licenses. Of course, if you have more developers working on OPC UA, we also offer you some site licenses.
Gotcha. All right. Well, we are at our time, and I want to keep to our time limit. I want to remind everybody that this presentation has been recorded, and all of it will be available on an on-demand basis. You will receive an email, and the slides and the audio and questions at the end will all be available to be viewed at any time. On behalf of Automation.com and Softing Industrial Automation, I would like to thank you for your participation in today's event and urge you to look for that email in case you missed any portions of this webinar or would like to rewatch it. An additional reminder, please look for our post-event survey and take a few moments to let us know how we did so we can improve your experience next time. This concludes today's program, and I thank you for your attendance. Have a great day.